Hi everyone, my name is Miss Winslow. Welcome to your Reducing Radicals lesson. In this lesson, we are going to be covering a few things. We will first review perfect squares. This is something I'm confident you guys are going to be super familiar with. We're going to be simplifying radicals, looking at radicals with fractions underneath, and then doing something called rationalizing the denominator. So let's go ahead and get started. But first, why do we even do this? We often ask this in math class, and if you don't ask yourself this question, if you don't ask your teacher this question, you should. I encourage you, always ask why and how and when. And this particular topic doesn't really have a direct connection to something in your world or the real world. But the process that we're going to use is big brain thinking. This is going to take you to problem solving methods and heights. So these are tools that we're going to use as we move forward in mathematics to solve bigger and more challenging problems that are connected to our world. Excuse me. So in my opinion, that's what math is. It's problem solving. So you're presented with a problem, you go into your brain and into your memory and you access the tools and the processes that you've learned. You pick the right one, the one that you feel is going to be the best one for that problem. You apply it and then you get a solution. So in my opinion, this is the most powerful mathematics you can do because you can literally apply it to anything. So let's review perfect squares. When we look at this, we're trying to take the square root of 4, and I bet all of you instantly know the square root of 4. The square root of 4 is 2, and that's because you can write 4 as 2 times 2. It's considered a perfect square because you can choose, or not really choose, but you can find two numbers that are exactly the same that multiply together to give you that number. It's called a perfect square. And see, we have two numbers here. There's a pair of numbers. And so when you're taking the square root, that's what you're looking for. You're looking for two numbers that are the same. So let's try the second one here, the square root of 16. Can you guys think of two numbers that multiply together to give you 16 that are exactly the same numbers? And you likely already know this one as well, 4 times 4, right? So the square root of 16 is 4 because we have a pair of 4s. Let's try 25. Again, you guys already know this. It's 5 because we can write 25 as 5 times 5. We found two numbers that are exactly the same that multiply together to give us that number. Keep going. 100 is 10 times 10, right? So the square root of 100 is 10. And then the next one, let's try 81. Can we think of two numbers that multiply together that are the same that give us 81? And it is 9 times 9. So the square root of 81 is 9. How about 27? Can you think of two numbers that are exactly the same that multiply together to give us 27? And likely you're going, no, I don't think I can. And that's because 27 is not a perfect square. So you're familiar with taking the square root of numbers that are perfect. What we're going to review next is how to take square roots of numbers that are not considered perfect numbers. And you'll see how we do that. So let's look at 27. And the first step in doing this is, well, let's see, what times what is 27? If we can't think of two numbers that are the same, let's see what numbers that do multiply. So you can use your calculator for this to help you find those numbers if you need to. I typically just start with 2 and say, can I think of a number that multiplies together to give me 2 to 27? And you can't, right? 27 is not divisible by 2. So then I'll try 3. So what times 3 is 27? It's 9, right? 3 times 9 is 27. These are not the same exact numbers, so that's again why this is not considered a perfect square. So let's see if we can keep going with this factor tree. I'm going to circle the number 3 because 3 is considered a prime number. That means we can't go any further with it. There are no other factors. Like we can't go like this and find 2 other numbers that give us 3 besides 1 in itself, right? That's what makes it prime. So I called this my factor tree. You guys have probably heard of factor trees before. And then I circled the hanging fruits. So 3 is a fruit. We got to stop there. There are no more branches that are going to come from 3. I mean, technically you could write this if you wanted to, but you're really just writing the same thing, right? 3 and 3. How about 9? 2 numbers together that give us 9. 3 times 3. I'll circle those. So really, we can write 27 as 3 times 3 times 3. And so now, just like before, we're looking for pairs of numbers. Here's a pair. Check that out. Look, 3 times 3, that's 9. So I just wrote 3 times 3 is 9. Isn't 9 a perfect square? It is, right? 3 and 3. So we can go ahead and take the square root of 9. Let's take it out. The square root of 9 is 3. That'll come outside. But look, we just had 1 3 under here, so we're going to leave it. That's it. That's how you take the square root of a non-perfect square. It's called simplifying. So you're trying to find perfect squares within the number. See, let me get a different color. We found the perfect square of 9 within 27. So we were able to go ahead and take the square root of 9 to get 3 and leave the other part underneath the radical bar. Let's try it again. 28. You might already know 28 is not a perfect square, so we're going to break it down. We're going to see if we can find a perfect square living inside 28. So let's do our factor tree. 2 numbers that give us 28. How about, I initially thought 4 and 7. 7 is prime, right? We can't go any further with that. But 4, you might already see it, that's our perfect square that lives inside 28. Because here they are, 2 and 2. So we can really write 28 as 2 times 2 times 7. And we're looking for those pairs of numbers because that's our perfect square. If you want to, you can write this step here. Some people like to do that so they can really see that perfect square. Remember, 2 times 2, that's just the 4. You don't have to write this step. Again, some people are just super visual and they like to see where the perfect square is coming from. So now we can go ahead and take the square root of that part. The square root of 4 is 2. Take it out. And what's left? 7. There is our simplified radical. So that's all we're going to do for the next few slides is we're just going to do a few more examples. You guys can pause this recording at any time if there are no pauses built in for you at certain points. And then we're going to do a few other things. Let's look at 45. Can we think of 2 numbers that multiply together to give us 45? How about 5 and 9, right? 5 is prime, can't go any further, and we can break 9 down into 3 and 3. So we're going to write all of our factors here, our prime factors. I usually just write them in order and group things together. And look, here we go. Here's our perfect square that lives inside of 45. It's 9. So let's go ahead and take the square root of 9 out. It is 3 because 3 times 3 is 9. And we have 5 left underneath. Let's do our next example, example 4. I'm going to do a different color just to change it up a little. 125. Woo! Our numbers are starting to get bigger. Don't forget, you can use your calculator to help you find the factors. You can't use the calculator to solve this for you. because the calculator will give you a decimal. Like if we were to put 125 in the calculator and square root, you get 11.18. And we want to put this in simplified radical form because that's going to be the most simple, complete answer. You know, with decimals, we always lose some of those place values because we end up rounding. So a lot of the problems in your OMHS and in life, they're going to want the most complete simplified version. So that's why we can't just take the square root of it with the calculator. But we can use the calculator to help us find these two numbers. Like, let me see if 2 works. Nope, you get a decimal. So let's see if 3 works. Nope, you get a decimal. Let's divide by 4. Nope, you get a decimal. How about 5? Yep, 125 divided by 5 is 5 times 25. So see how you can use your calculator to help you find the factors? I circled 5 because 5 is prime, remember? That's one of our fruit. We can't go any further with that, but 25, maybe you already see it. See, there's the perfect square that lives inside 125. We can keep going though to get all of our factors. So we have 3 5s here, and we're looking for pairs of numbers that match. That's that perfect square. If you want, you can rewrite that perfect square and go ahead and take it. The square root of 25 is 5, and we have 5 left underneath. You can always double check your work by placing this in the calculator. If we do 5 root 5, oh, you get the same thing. So that's just a good double check way. If you put root 125 in the calculator, you get 11.18. And if you put 5 root 5, you get 11.18. So you definitely simplified properly, correctly. But again, we want the radical form. It's the most complete. And again, as you move on in math, especially into geometry and algebra 2, well, and algebra, of course, you're going to see that we're going to use radical forms of numbers a lot more than decimals, really. Let's try 550. They're just getting bigger and bigger. So you guys probably know from back in the day that when a number ends in 0, you know it's divisible by 5. So we could try 5. And 5 worked. 5 times 110. Okay, let's keep going. I wonder what else will work with 5. 5 and 22 is 110. All right, and then 22. Is 22 done? What can we divide by 22? We could do a 2, and that would give you 11. 2 times 11 is 22. And we know 11 is prime. So I'm just going to double check 5 times 5 times 2 times 11. 550, yep. Here are all of our prime factors. If you were to take all of these numbers and multiply them together, you would get 550. So we really didn't change the value of anything. We definitely didn't change the value. We're just changing the way it looks. We're sort of rearranging it a little to find a perfect square that lives inside the number. And here it is. Here's our pair of numbers, our pair of 5s. So if you wanted to, we could write that as 25. You can see the square root of 25 is 5. Take it out. And what's left underneath? We have a 2 underneath and we have an 11. So we have 22 underneath. Here we go. You can write root 550 as 5 root 22. All right, let's look at our first example with a fraction. So I just wanted to show you guys this because sometimes when people see this problem, they get a little confused, but it's really not too bad. When you see a huge radical bar like this, all you can do is rewrite it like this. The radical bar goes to each number. And then we can just work with the numerator and the denominator separately. So the square root of 16, we know that is 4, right? And because, remember, it's 4 times 4. There's our pair of numbers. And 9 is 3 times 3. So the square root of 9 is 3. And you're done. So whenever you have a big radical bar going over the entire fraction, you can just put it on the top and on the bottom, and then deal with each part separately. Looks like we have the same example here. Sorry about that, you guys. So we have 4 over 3 again. Let's try this one. We're going to have radical 25 over radical 3. So the numerator, we know that radical 25 is 5 over square root of 3. Now there's something really important about this example. You can see we have a root or a radical in the denominator. And there's something that mathematicians like to do, and it's called rationalizing the denominator. Again, you're not really going to see rationalizing the denominator as a step that you'll take for something in the real world. However, the process in which you do it builds your problem-solving skills to be able to attack any problem in the future. So the process we're going to learn here is building our abilities to solve problems. I'm talking any problem. Changing a tire, finding a job, building a house, buying a pet. Any problem involves mathematical problem-solving skills. So the point here is we do not want to have a radical in the bottom of a fraction. It makes the number irrational. So we want to rationalize it. And here's the process to rationalize the denominator. All you do is multiply the top and bottom by whatever this is. Root 3 over root 3. So if that was a root 6, we would multiply by root 6 over root 6. If it was a root 207, we would multiply by root 207 over root 207. So whatever's in the denominator, you're going to multiply the entire fraction by that. And we're not changing the value of it, right? Because look, root 3 over root 3, that's just 1. So we're really just multiplying by 1. But we're going to change the way it looks. We're manipulating it. So when we multiply, we're just going to do the top times the top, 5 root 3, and the bottom times the bottom, root 3 times root 3. All right, so we end up with 5 root 3 on the top, and then we're going to have root 9 on the bottom, right? Because 3 times 3 is 9. If you look at this, what is the square root of 9? The square root of 9 is 3, right? And that's the whole point when we're rationalizing that denominator is to multiply it by itself to get rid of the radical because we have a pair of 3's here. And we are finished. 5 over 3, that cannot be reduced any further. Let's look at the next one. Okay, so the cool thing about this problem, and I think any math problem, is that you guys have the ability to choose. So we can choose to rationalize the denominator first. So you see that radical down here, we know we need to get rid of it. Or you can choose to simplify the radical and then rationalize. Because as these numbers get bigger, it's very likely that they'll be able to be reduced. And maybe you're already seeing what this could be written as. So I'm going to do it both ways so you guys can see the difference in the options that you have. Let me get a different color. There we go. Okay, so 24. We got to think of two things that multiply together to give us 24. And I initially thought of 2 and 12. Maybe you thought of 6 and 4. Totally fine. And we're going to end up with the same answers. We're going to circle 2 because that's prime. Remember, we can't go any further. 12 is 2 times 6, and 6 is 2 times 3. So there we go. We have our prime factorization of 24. 2 times 2 times 2 times 3. So with square roots, we're looking for pairs of numbers. Here it is. There's our perfect square. 2 times 2 is 4. So we can go ahead and take the square root of 4. We'll take it out. It's 2. And what's left underneath the radical? We have 1, 2, and 1, 3. So that is our 6. So now from here, remember, because the 2 is out front, it's being multiplied, we can go ahead and reduce the 12 and the 2. So 12 over 2, that's 6. And now the numbers are getting much smaller and much more manageable. We're going to go ahead and rationalize the denominator. We're going to multiply the top and bottom by whatever is in the denominator. So we'll just do the top times the top, that's 6 radical 6, and the bottom times the bottom, square root of 36. And remember, that's the whole point, right? Because you're like, wait a minute, square root of 36, that's 6. So this is really going to equal 6 root 6 over 6. You guys know this can also be reduced. 6 over 6 is 1. So our final answer is root 6. This whole thing reduces down to just root 6. And we could put this in our calculator if we wanted to. 12 divided by root 24 and root 6, and you would get the same exact decimal. So that's a nice way to sort of double check your work. But don't forget, sometimes problems are going to want the specific radical answer. So that's one of the reasons why we learn this process. Because radical answers are a lot more specific than decimal answers. When we have decimal answers, we often round them off, right? So you lose some of those place values. With radical answers, you don't lose anything, so it's much more accurate. Let's try it the other way. So if you have a radical in the denominator, maybe that's the first thing you see, and you're like, hey, I got to rationalize that. So you multiply the top and the bottom, that's a 24, by the radical that's in the denominator. So we have 12 times root 24. And then, what is 24 times 24? See, I don't even know. I'm going to grab my calculator. That's a big number. It's 576. But the beauty is we know the square root of 576 is 24, right? Because that is the perfect square. So really, we're going to have 12 over root 24 over 24. I don't know why my 4 keeps connecting itself. Okay, so now we can reduce. 12 goes into 12 once, and 12 goes into 24 twice. So we get root 24 over 2. We're almost done. This is where we would look at root 24 and be like, okay, 24, that's a pretty big number. I wonder if it simplifies. And it does, right? We got the prime factors of 24 already. Of course, you would just do that process again. We don't have to because we already did it. And there's our perfect square. Take it out. So we end up with 2 root 6 over 2. Check it out. These cancel and we're left with root 6, just like we got doing it the other way. So again, that's the really cool thing about mathematics, and one of the reasons why we study reducing radicals, because you'll be presented with some problem right here, right? And then you'll go into your brain, you'll access all of the tools, all of the procedures, all of the mathematics, all of the thinking, and you'll develop your very own path to get through it, to solve it, to get to your light bulb moment. So even though the process of reducing radicals might seem, I don't know, trivial or that it doesn't have purpose, it truly does. You are building those brain muscles to be able to solve problems. So that's really cool. Thank you guys so much for watching. Bye, everybody.